Welcome back to this next video in which we're discussing finite dimensional vector spaces. Okay, so we're in the process of proving that if you have a vector space capital V, which is a finite dimensional vector space, and you have a subspace capital W of this vector space capital V, that this subspace is also a finite dimensional vector space. Okay, so I'll copy now the picture of my subspace out down here, and we will now actually prove this result. Okay, right, so we'll have my subspace capital W here, we'll have the entire vector space capital V here. So I'll outline capital V in red here. Now remember, the definition of being a finite dimensional vector space is that you must have some set of vectors which is finite and which spans the entire vector space. So I'm trying to find a finite set of vectors which spans my entire vector space capital W. Okay, so I'm now going to attempt to construct such a set. Okay, right, so first of all, what I want to do is firstly start off by taking a vector from my subspace capital W. So I'm trying to construct a set of vectors which is going to span the entire vector space capital W. Okay, so the first thing that I do is I have to start off by putting a vector into this set. Now there are two possibilities here. Either this subspace is the silly subspace, which is the zero subspace, which contains just the zero element of the vector space capital V. Okay, so if this is the zero subspace, then of course there's only one vector in it. Okay, and that vector is equal to 0. Okay, now if that's the case, then I can put 0 into my set. Okay, and now I'm done, because I've got the only vector in the subspace capital W in this set. Okay, this set will span the entire subspace, and it is a finite set. Okay, so if your subspace is the really stupid one, the zero subspace, then the only element it will contain is 0, but that's okay, we can just put 0 into a set. That's a finite set, okay, and it spans the entire subspace. So indeed, this subspace was a finite dimensional vector space. Alternatively, however, it won't be the zero subspace, and instead we will have some element which is not the zero vector, which we'll call little w. Okay, and I'm going to start by putting little w into my set here. Okay, now we know that whenever you have a set containing just a single vector like this, it is a linearly independent set, so I can call this L. Okay, providing that vector isn't the zero vector, which I've said it now isn't, this is going to be a linearly independent set of vectors. Okay, right, now here's the really important thing, that if a set is linearly independent in the subspace capital W, it's also going to be linearly independent in the larger vector space capital V. Okay, so this is a really important concept, and it has to do with the fact that we haven't actually changed the field when we restricted down the composition law of scalar multiplication. Okay, so this is a subset of vectors of the larger vector space capital V, as well as being a subset of vectors of the vector space capital W, and in both of those vector spaces it is going to be a linearly independent set. Okay, because remember, what does linear independence actually mean? It means that there can be only one linear combination which gives the zero vector. Well, a linear combination of a set of vectors means exactly the same thing between the two different vector spaces. Okay, so if it's true in one of them, it will be true in the other. Okay, so if I have a set of vectors from the subspace capital W which is linearly independent in W, that will also be a set of vectors in the larger vector space capital V which will be linearly independent in that larger vector space capital V. Okay, that's really, really important. Okay, so this is a set of vectors which is linearly independent in the larger vector space capital V. Okay, right, and we'll come back to that in a moment. Now what we're going to do is we're going to extend this up to form a basis of the vector space capital W. Okay, so we're going to gradually add vectors into this. So either, well, the same argument that we've done just above will apply here. Either the span of this set here will be the entire subspace capital W, or there will be some vector outside of the span of this set which I'm going to add in, and it will remain linearly independent in W. Okay, but remember that's also going to be a set that's linearly independent in V. Okay, and what I'm going to continue doing is building this up to form a basis of W. Okay, and every time I add more vectors in, it will still be linearly independent in W. We're doing exactly what we've done here, but remember, if it's linearly independent in W, it's also linearly independent in V. So all of the steps, all of the bigger sets that I'm forming that are all still linearly independent in W, they're also linearly independent in V. Now, what do I know about linearly independent sets in V? Well, I know that linearly independent sets in V have order less than or equal to the dimension of V. So all of these linearly independent sets that I'm building here are going to have order less than or equal to the dimension of V. Okay, even once I get up to the full basis of W, this must be less than or equal to the dimension of V. I cannot continue adding vectors into this set and it remaining linearly independent forever. Okay, I will end up getting to an end at some point. Okay, and it will have to be before the dimension of V, or at the very latest at the dimension of V. Okay, so I hope you understand that argument. Okay, it's because if I've got a set of vectors in W that is linearly independent, it's also linearly independent in V. We know that all sets that are linearly independent in V have order less than or equal to the dimension of V, which is a finite value. Okay, so I'm now just going to extend this linearly independent set here up into a basis of W, okay, by adding more and more vectors outside of the span of L. Okay, all of those things that I construct are going to be linearly independent sets. I must eventually reach something that spans L, that will be the, spans W, that will be the basis of W, and that must have order less than or equal to the order of the dimension of V. Okay, so firstly, this now proves that this subspace W is also a finite dimensional vector space because I've got a set here which spans the entire vector space, which has a finite number of elements in it. In addition, of course, the size of the basis of W is what we would call the dimension of the subspace W. Okay, so indeed what this now tells us is that the dimension of a subspace W is actually less than or equal to the dimension of a vector space capital V. Okay, right. So that then is an extremely important theorem about the dimension of subspaces of vector spaces, that the dimension of a subspace capital W is always going to be less than or equal to the dimension of that vector space capital V. Okay, right, and with that then we will end this video on finite dimensional vector spaces.